Hey guys, today we're going to look at how to work with systems of inequalities. And so what we'll do in this lesson is learn how to graph those systems and then use that graph to identify solutions to the system. So if you remember, an inequality is just like an equation. They're equal signs. Inequalities have those greater than or less than or greater than or equal to, less than or equal to symbols. And so we've already looked at how to graph linear inequalities. And you remember that you have either a solid line or a dashed line, and it shades on one side. And anything that's in that shaded area counts as a part of the solution. Well, with systems of inequalities, it's very similar, but instead of having just one line that is graphed and shaded, you're going to have two. And so it makes it just a little bit different to look at the area that is considered the solution. But it's really kind of the same process that what we did when we did single inequalities. Just now we're going to look at two instead of just one. So let's get into this. So a system of inequalities is a set of two or more inequalities with two variables, just like a system of equations. Systems have many solutions. So, in a system of equations, the solution is that one point where those lines cross, period. But in systems of inequalities, there are many solutions. Just like in regular inequalities, there's so many points that could fall in that shaded area. In systems, there are many points that could be solutions too. But they're still points, so systems have many solutions, but those solutions are still ordered pairs. Those solutions represent points where the solution sets intersect. The x and y values that make both inequalities true, or the x and y are the values that make both inequalities true at the same time. All right, so let's look at things that we want to remember about inequalities. And this kind of references back to the work we did with single inequalities. But things to think about: a dashed line means points on the line are not included in the solution set. A solid line means points on the line are included in the solution set. And if you end up with a system that has no areas that overlap, then it has no solution. The only way you would end up with no solution would be if you ended up with parallel lines that were shaded on opposite sides. Like if one was shaded above it and one was shaded below it and they never touched. It is possible to have parallel lines that touch because they're both shaded to the inside. And that would not be a no solution situation. But parallel lines that are shaded to the outside on both, that would be your situation of no solution. So that would be like if you had, and you don't have to draw this, but just to remind you, if you had two parallel lines like this, and one was shaded up here, and the other one was shaded down here, those would never interact because they're never going to touch each other. That's your situation of no solution. All right. So here's how we solve a system. Simplest way is to just graph it. And I'm not going to ask you to graph them by hand. We'll use Desmos because why not? Biggest thing to be careful with this is making sure you type it in correctly. Use the right sign. Make sure that you type everything in the way that it's written. But use Desmos to graph both lines together. Then find the points where the solution sets overlap. So you're going to end up, and again, you don't have to draw this, but I just want you to see it. You end up with one line go in one direction. And you'll have another line that crosses it some way. But with inequalities, you're going to have shading. So my red line, for example, might shade on this side. And my blue line might shade under here. And this doesn't do a great job showing it because it doesn't blend the colors. But you can see that this area right here would be shaded in both colors, right? Can't really make that work, but so this area is the solution. So whatever points would fall in that area that ended up shaded both colors would be considered the solution set for this. Any point that falls in that section. It's not just about the point where they intersect. It's about any points that fall in that overlapping area. All right, so let's look at some examples of this. So here I've got two different examples of systems of inequalities, and I've got some ordered pairs I want us to check and see if they're in the solution set or not. So the first thing we're going to do is pull up our Desmos. And we're going to type those two systems in. So negative x plus y is less than or equal to 3. And 2x plus y is less than 0. Okay, so here's the graph of our solution set. And let's just look at kind of what we can see from this before we actually start looking at our points. So what we see is we've got two different lines shaded here. I've got my blue on this side. My red has been shaded here. I could see that this area is the area that is shaded in both colors. So anything that falls in this area is what's going to be considered part of the solution. In addition to that, anything that falls on this solid line that is the boundary for this area would also be considered a part of the solution. Things that fall on this dotted line as a boundary are not. So anything here would be a yes, anything here would be a no. Points up here on the solid line are also a no, because they only work for the red, they don't work for the blue. A point that is the point of intersection, like this point of intersection right here, is not a solution unless both lines are solid. So because a dashed line goes through it, it's automatically eliminated there. So, but any other point that falls in that double shaded area would work. So what we can do is we can look for our ordered pairs. Now, if you're good with coordinate plane and you can just look for them on there, great. If you need to type them in like this, you can type them in and it'll graph them for you. I'm just going to graph a bunch of them. And you do have to put parentheses around them to be able to graph them, by the way. Okay, so there's our first three. And looking at those, look at where those points fall. I want to see if any of them are solutions. So to be a part of the solution set, they have to either be in the double shaded or on the solid line boundary of the double shaded area. So for these first 3 points that I've just checked, 2 are only shaded red, so both of those are out. And this one is on the dotted line, so it is also not a solution. So this is a no, this is a no, and this is a no. Let's check the others. -2, -5. -3, 0. And 0, 3. Alright, so looking at those, see we've got one that's in the double shade. We have one that's on the solid line, and we have one that is outside. So we know that 0, 3 is not a solution, but both the others are good. So we can eliminate that one, but both of these would be solutions to this. So that's how we're going to go about answering those. We're going to graph them in Desmos, and we're going to look for points that fall in that double shaded area or points that fall on the solid line. Not on a dashed line and not outside. Let's do another one. Oh, well, that's pleasant. I don't know that I can do anything about that. Oh, yes, I can. Or not. Well, oh, there we go. Okay. All right, let's do the same thing with these next ones. So 2x plus y is less than 1. Y is greater than -2x plus 4. Y is greater than -2x plus 4. Okay, there's what I have graphed. Now, you may be able to look at this and automatically know what your solution will be. And if you see that, at no point do any of my double shaded areas overlap. Now, if I zoom way out, it looks like I just have one single line there, but we don't. So our lines are parallel and they're shaded on opposite sides, which means none of these points could be solutions because there are no solutions to this. So if you see something like that where they shade on opposite sides and the solution sets never touch, then you know you're going to have a situation of no solution. All right, let's do a couple more and then I'm going to let y'all try a couple. All right, same deal. Get Desmos. X plus y is less than 2. And y is greater than or equal to 2x minus 5. Okay, so here's what we got this time. And again, you can see where the shading is the same in this area over here. You can also see where we've got a dashed line up at the top of that boundary area, and we have a solid line at the bottom. That tells me that any point that exists here is not going to be a solution. Any point that exists here is. This point, my point of intersection, is a no because the dashed line runs through it. So I'm only looking for things that are on this area or on this solid line here. So I'm going to check all my points. So 0, 0, 5, 2, 5, -5, -2, -5, -5, 0, and 0, -5. Okay, there's all the points. So, from all of this, we can definitely see that there are some points that are not in the solution set. And then we've got some that are. Looking at what we've got here, 0, 0, our point at the origin, that's the first one we started with, is here. It's definitely in the set, it's in the double shaded area. 5, 2, which is this one. So 0, 0 is done. We'll take it out. One less thing to look at. 5, 2 is definitely out. So that's a no. 5, negative 5. It's our black point right there. Also not in the double shaded. It's only shaded one color. So that's out. Negative 2, negative 5 is good. Negative 5, 0 is good. And what about this point right here, that green one? So it is on the line, but because the line is solid, we can count it. So all three of those points are in the solution set. All right, we're going to do one more together and then let y'all try a couple. 2x plus 3y minus 9 is greater than or equal to 0. X plus y minus 6 is less than or equal to 0. And no offense to the color black, but it's hard for me to see the shading when it's like that. So I'm going to go it's a little bit brighter. I'll go with blue. Okay, so here is my graph of this. So looking at this one, the parts that are shaded, both colors exist right here. So anywhere from this little spot right here on up through all this area. And it would get wider the further up we panned. Maybe if I can actually scroll. Anyway, I can't scroll over there, but it would get wider the further that way we go. But what we can see from that is that they're both solid lines. So we know that we've got anything that's on the line is going to count. Also, for this, our point of intersection here will count. Because both lines are solid, we can count that point as a boundary. So anything in the double shaded area or on the solid line, including our points of our point of intersection, will work for this as solutions because all the lines are solid here. So let's test our points and see what we end up with. Let me see if I can move this where we want it. Maybe not. I don't know. I can't get that to go away, but it doesn't really matter. I think we can function around it anyway. So if I'm testing the points for this, 0, 0 is first on my list. I always test 0, 0. 5, 0. 0, 6. 9, negative 3. Negative 3, 0. And 0, 3. That's all of our points. Alright, so for this one, looking for the points that fall in the solution area for sure. And so as I look at this, I can see that 0, 0 is definitely a no. Right? Because it's falling right here. So 0, 0 is out. I also can see that negative 3, 0 is out. Both of those are outside of our solution area. So negative 3, 0 is also a no. Now these other points, I've got this one that's definitely inside at 5, 0. I have these other three that are all on the line. But because the lines are solid, all three of those will count too. So all four of the remaining points are part of the solution. Because they can be on the solid line boundary or they can be in the shaded area. And all of that will count. All right. Okay, so I want y'all to try these two. Take just a minute. Go to Desmos and graph these two systems. Check those points and see which of those points are a part of the solution set for these. And then I'll come back in a few minutes and we'll talk through what the correct answer should have been in this space here. Okay, so that should have been enough time for you to graph and check the points for both of those systems. And if you did that, you found that in the first one, the only point that was in the solution set was 0, 0. None of the others were a part of that, oddly enough. And then in the second one, you found that only 2 points were in the solution set. 1, -3, and 2, -5. Everything else was outside. if you did not get those as answers, go back and take a look at your goals again and see if you can see maybe what you did wrong. If you chose points that were on the dash line when you should have been choosing points in the shaded area or on a solid line, that might have gotten you. Or maybe you were looking at things that were only shaded one color by mistake. Otherwise, that's what you should have gotten for that. Okay, so that's the basics of if they give you a system and you're looking for the solutions, that's what we're doing. Now, they also can give us some word problems. And so if we're given word problems, we may have to create a system of inequalities for that. So we're going to treat this just like we did yesterday when we were writing our systems of equations. But now instead of using equal signs, we're going to use inequality symbols. So I've got just a couple of examples of that. I didn't want to do a whole bunch of these because I'm not there today. And because it's really the same thing we did yesterday. We're just using some symbols instead of equal signs. But here we go. Aiden works at Meridian Cycles. At the dealership, he sells 2 scooter models, a $5,000 standard model and a $7,000 racing model. Last month, his goal was to sell at least 36 scooters. So I'm going to highlight that because that tells me one of our inequality symbols that we need. If Aiden met his goal and brought in over $250,000 in sales, well, there's our second inequality, over $250,000 in sales. We're to write a system to represent the situation. So I've picked out those 2 things that were totals in this problem. And so our totals were at least 36 scooters. At least, remember, means that much or more, which means what he sold had to be greater than or equal to 36. And then he met his goal and brought in over $250,000. That means what he brought in was greater than 250,000. So when I go to set up this system, I need to look for words that tell me what symbols to use and what will go right beyond that. So I've got this. Now let's talk about what this means. The 36 is the number of scooters he sold. So we can write an inequality that shows that he could sell X standard model scooters plus Y racing model scooters to get that 36 scooter total. So X would be standards and Y would be racing. And then the one about 250,000, that's money. So that's where our money's going to play in. $5,000 for each standard model plus $7,000 for each racing model to get $250,000 total. And we could graph that and find points that would work in that situation, but that's not what we're doing. We're just creating the system here. All right, let's look at another one. Ava has 2 jobs. She works as a barista, which pays $13 an hour, and she works as an illustrator, which pays $30 an hour. She wants to work no more than $45, so I'm going to highlight that. $45, 45 hours. No more than 45 hours. And to earn at least $625 per week. At least $625 per week. Her barista job schedules her for up to 30 hours each week. So there's another constraint on that. Which of these systems represents the situation in terms of X and Y, where X is the number of hours she works as a barista and Y is the number of hours she works as an illustrator? So looking at this information that is given to us, we're going to have 3 different inequalities because we have 3 different constraints here, which is why we've got all this stuff that's going on here. So let's start with what we know. She wants to work no more than 45 hours. So no more than means exactly that, not more than. So if it's not more than, it has to be less than or equal to. So we know that this part, not more than 45, means we're going to be less than or equal to 45. And that's going to be between both jobs. She's got 2 different jobs. So if X is barista and Y is illustrator, that means the 2 together have to be less than or equal to 45. So from the beginning, I'm going to eliminate things that are not showing that one. So A shows x plus y is greater than or equal to 45. So A is out. B shows x plus y is greater than or equal to 45. So B is out. C uses less than or equal to, and so does D. So it could be either one of these at this point. So now we go on to our second thing that we know. She wants to earn at least $625 a week. Now, at least means that much or more. So, at least would be greater than or equal to 625. And again, what she's earning is coming from both jobs. She's making 13 an hour at one, and she's making 30 an hour at the other. So 13x, I didn't leave myself enough space here, y'all. Plus 30y. Together, it needs to be more than or equal to 625. So again, I'm going to go look at my answer choices that are left. This one uses the greater than or equal to. This one uses less than or equal to, which means my answer must be C. And it's not D because you used the wrong symbol. And so that third inequality, well, it doesn't matter because it's the same for both of these anyway, shows that she can go up to 30 hours a week. That means she can't go over that, which is why it has that less than or equal to 30 in this space here. So the correct answer to this one would have been C. Look for those words that'll tell you what symbol to use. If you can't remember what symbol, really think about in your brain, does this mean I can go more than this? Or does this mean I have to stay less than this? What side of that can you be on? And then you can kind of use your symbol from there. All right, take a minute. See if you can figure out an answer to this. You may have to write a system of inequalities and then check and see which of these would work in that system. You might find another way to work through this. It does not matter to me how you do it, as long as you can come up with a correct answer that mathematically will work every time. So take just a few minutes or a minute or so and see if you can come up with an answer to this one. And then we'll come back together and see if you get it correct. All right, let's go back together on this one. Hopefully, if you worked this out correctly, you got an answer of B. And there are a few ways you could have done that. You could have tested out that if you had 16 of these 80-pound packages, you could have done 16 times 80 and then added to that enough 50-pound packages to reach 20 packages total and made sure that it stayed within that 1,500-pound limit, which 16 would have done. 15 also would have done that, but 17 and 18 would have gone over. I wrote a system for this, and so my system looked like X plus Y. I let X be 50-pound packages, by the way, and Y be 80-pound packages. So I let X plus Y be greater than or equal to 20, because you had to have at least 20 packages. And then I let 50X plus 80Y be less than or equal to 1,500, because they couldn't exceed the goal or the weight of 1,500 pounds. And from this, I used these as points, but I had to know the X value to go along with these as Y values, because these were my 80-pound packages. So if I knew I had to get at least 20, and there were 15 80-pound packages, I knew I would have had to have 5 of the others. So I checked the point 515 to see if it would work. Then I checked the point 416 to see if it would work. Then I checked the point 317 to see if it would work, and 218 to see if it would work. And neither of these was inside of the shaded area. These both were, but they wanted the greatest number, maximum number, so 16 would have been the most. So if you're going to do it with a system, you have to know the entire ordered pair to check. So if you only know half of it, you need to figure out what the other half would be based on the limits they give you. So if the limit was 20 packages, I would have to figure out what would be required to make that happen. All right. Now, the next few questions are test prep style questions. So I'd like you to take just a few minutes and work through those next 4 slides. I think it's 4 slides that say test prep. And then we'll come back together with the answers to these to check them. And then you guys should be good to go. So take a few minutes to work through those next ones, and then we'll come back together and see if you are correct. All right, let's talk through these. You should have been hopefully finished with them by now. So the first one, you should have found that the solution was 3, 0. None of the other points fell inside of that double shaded area, but that one was. So that was the correct answer to that. For this one, the system you should have chosen was B. And the reason we know that is because up here it says that she wants to earn at least $65. And then she can work, the most she could work is 15 hours. So if she can only work up to 15 hours, the amount she works has to be less than or equal to 15, which is what that showed. And at least 65 means she wants to earn that much or more. So greater than or equal to 65. The 5x and the 7x had to go with the 65 because that was money and 65 was money. So B is your correct answer on that one. On this one, if you graphed them and then you looked at these, oh, you know what? I just messed this up. This says which statements are not valid. And I picked the ones that were valid. So there's that. Valid means true, by the way. C and D were true. A, B, and E were not. So your correct answers here should be A, B, and E because all of those are not true about that solution set. 5, 0 fell outside. Line 2, or inequality 2 had a dash line. And because inequality 2 had a dash line, the points on the line were not solutions. So A, B, and E were all not true statements. And then the last one. I'll ask you to pick the system of equalities represented by this, and you really just had to graph all of them, and really it was the same thing over and over, just change the signs, and see that third option would have been the one that created this. Now, in this one that they've created, they didn't show the rest of the shading. So there would have been a part that was shaded just one color right up here, because it would have shaded across all of this. And there would have been a part that was shaded just one color here, because it would have shaded across this. But this would have been the double shaded area, so this is the solution set for it. So they only shaded the one area that would be considered the solution set instead of showing you all the shading. But same idea, same concept there. All right, that's the end of our little lesson on solving systems of inequalities. You'll have a graded practice on this, and that'll be the end of all of that. Y'all have a beautiful day. Thank you.